In the last lecture, we started to look at the factors which influence the intensities of diffraction peaks. In this lecture, we're going to continue that journey by looking at the structure factor. All right, so this was the equation that contained all of the terms that might influence the intensity of a diffraction peak in a powder diffraction pattern, or if we were to take away the multiplicity factor, would be applicable to a single crystal diffraction pattern. But in the last lecture, we more or less said we're going to delay talking about this term F squared, the structure factor. But without a doubt, the structure factor is the most important term in this equation, because as the name suggests, the structure factor contains all of the information about the crystal structure, about where the atoms are located in the unit cell. So in this lecture, we're going to delve into the structure factor. It's a little more complicated than the other terms, but that extra effort to understand it is worth it. Before we get into the structure factor per se, it's helpful if we review some of the properties of adding or combining waves. Let's start by looking at how we might add together or combine two waves. Each of these waves is a cosine wave, and each wave can be defined by the wavelength, the amplitude or peak height of the wave, and then what's known as the phase shift. So let's explain each of these. I think the wavelength should be familiar, and in this example and everything that follows, we're going to talk about combining waves that have the same wavelength. That's the situation we have when we're talking about diffraction using monochromatic radiation. The amplitude here is just the height, and then there's the phase shift. So what is the phase shift? Well, if we look at the wave shown in blue, where we're calling the phase shift 0, right, this is just a perfect cosine wave. It starts with its maximum value at 0 degrees, and as we go to 90, the value of the wave goes to 0. At 180, it's -1, and then it repeats. All right, this is a cosine wave. But if we were to take that wave and shift the starting point from 0 out to here, and here in this case would be 90 degrees, or pi over 2 in radians, we could think about it being the exact same wave, but just starting at a different point. All right, and this phase shift is what's going to happen when waves have different path lengths, which is exactly the case that happens during diffraction. Now, if we were to add these two waves together, the resultant wave would have the same wavelength as the two waves that combined. But what is different is that we have a different amplitude and we have a different phase shift. So when we add these two waves together, the maximum now is above 1. It goes up to 1.41, and that happens at an angle of 45 degrees. You can kind of see that if you look back here. This wave is dropping, the blue wave is dropping, and the red wave is rising, and they combine to reach a maximum here at 45 degrees. So we would say this new wave, the resultant wave that comes from adding these two together, has an amplitude of 1.414, has a phase shift of 45 degrees, and the wavelength is the same as the two waves that we added together to get this wave. Now, to create this figure, I just took these waves and generated them in a spreadsheet, and then I added them together. And of course, we could do that for any number of waves, but it's a little tedious or labor-intensive to do that when we're adding together many waves. So is there an easier way that we can use to combine waves? Well, the answer is yes. Okay, and we're going to do that by a way that might not be terribly intuitive to you. We're going to map each wave onto this kind of plot, which contains a real axis as the horizontal or x-axis and an imaginary axis as the vertical or y-axis. All right, so we're going to represent each wave with a complex number. And how do we represent this wave on this plot? Okay, the amplitude of the wave gives us the length of the vector that's going to start at the origin. This circle that I've drawn here has a radius of 1, and the amplitude of both waves is also 1. So that means that both arrows representing waves 1 and 2 are going to start at the origin and end on the circle. So that's the first lesson. The amplitude dictates the length of the vector. The other thing you need for a vector is a direction, and the direction of the vector is going to correspond to the phase or the phase shift of the wave. So the first one has a phase shift of 0, and so we draw it horizontal. The second one, the red wave here, has a phase shift of pi over 2, or 90 degrees. So we're going to represent that as a vertical line. The phase shift phi is going to determine the direction we draw this line. And here we have a 90-degree value for phi. You might think about it in another way. We could say this horizontal wave is a perfect cosine. And if you look at it for a minute, this red wave, right, which starts at 0, rises to its maximum at pi over 2, right? This is a sine wave. So sine waves are going to appear as vertical in this complex dimensional space, and cosine waves are going to appear as horizontal, and most waves are going to be somewhere in between, so they will be neither vertical nor horizontal. Now, if we want to get the amplitude and phase of this green wave, what we have to do is we have to do vector addition with the red and the blue. So if we take wave 1 plus wave 2, we end up at this point, and now the vector that represents the resultant wave, wave 3, is going to be from the origin to that point. And so if you look at this for a minute, you could say, all right, I've got a 45-degree right triangle here. So the length of my hypotenuse is going to be square root of 2 times my base, 1.414. That is the amplitude of the green wave. And the phase shift, phi, is going to be 45 degrees, which is exactly what we get. Now we can write this in a couple of ways. We could write the amplitude times cosine of the angle phi, right? That's really going to give us the length of this horizontal axis of the triangle, plus I is the square root of -1, that's what makes it a complex number, times the sine of the phase shift phi. That's this leg of the triangle. All right, so we're going to represent waves in this way. And really, when we see that notation, it's going to tell us, here's the amplitude of my wave, and phi, here's my phase shift. Now, Euler's relationship tells us that we could write this complex number in a more compact form, which is just A3 times e to the I phi. And we're going to use that more compact exponential notation quite a bit as we go along. Let's do one more example on wave addition before we leave that. The example I just chose was pretty simple. What if we wanted to add together 3 waves of different amplitudes and different phase shifts? So I've drawn them here, the blue, the red, and the green. Wave 2 has an amplitude that's only half of wave 1, and it's phase shifted by 30 degrees. And then wave 3 has an amplitude 50% bigger than wave 1, but phase shifted by 120 degrees. If I just add these together in a spreadsheet, I would get this wave. And if I looked at that wave more closely, I would say, all right, the maximum is at 1.69, so that's its amplitude. And this initial starting point of the wave is shifted by 68 degrees from 0. Okay, so it's got a phase shift of 68 degrees. And no matter how many waves I add together, I'm going to get a resultant wave with the same wavelength, but with a different amplitude and phase. Now you can imagine that it starts to get laborious to add all of these waves together. Let's see if we could get this same wave using our complex number approach. All right, so wave 1 is horizontal, phi is 0, and it has a length of 1 because that's its amplitude. Phase 2 is shorter, but inclined at a 30-degree angle with respect to the x-axis. And then wave 3 is the longest of the 3, and it's going a little bit backwards horizontally because it's at a 120-degree angle from the x-axis. And the resultant wave, we start at the origin and draw out to the endpoint, and this is our wave. Now, if I were to get out a ruler and measure this, I would see that the amplitude of that wave is 1.69. That's the length of this vector. And the angle is 1.19 radians, or 68 degrees. So that matches what I got when I just added the waves together in a spreadsheet. So this way of adding the waves together is actually a very convenient or clever way of seeing what the waves that come out of this addition process are. And we call this kind of approach an Argand diagram. Now, when we talk about crystals, what we're going to see is that every atom in the unit cell scatters the waves in a somewhat different way, with a different phase and a different amplitude. So these vectors, the blue, red, and green, those might represent the scattering from different atoms in the unit cell. And at the end, when we've added them all together, we can get the amplitude and phase of the scattered vector from this Argand diagram. All right, enough of the wave tutorial. Let's go back to diffraction. Okay, so this is our familiar picture of Bragg's law. Here I'm illustrating a very specific reflection that we get from Bragg's law. That would be the 100 reflection. And so this shape that I've highlighted in blue over here, this is the unit cell. And the A axis is vertical, and the B lattice vector is horizontal, and then the C lattice vector is going to be going, let's say, in and out of the plane of the board. We know from Bragg's law that the path length difference between wave 1 and wave 2, which is shown in red here, is simply equal to 2d sine theta, where d is the spacing between these planes of atoms. Now here, because I've chosen a specific set of planes, this d value, the d100, is going to be simply the length of the A lattice vector. All right, so lambda, which is the extra path length here, is going to be equal to 2a sine theta. And that relationship has to hold in order for constructive interference to occur. Now what happens if we insert another layer of atoms somewhere in between these two? Let's just pick an arbitrary position. I'm going to put the atom below the top layer by, I don't know, about 20-25% of the way to B. Now the distance between the top layer and this new layer that we've inserted, we're going to say that distance is x. All right, now let's think about the x-rays that are coming in at this angle theta. There's no reason why x-rays can't be scattered off of this intermediate layer, and in fact they will be. But if you think about the path of x-ray 3, you can see that the extra path length it travels compared to wave 1, which I've shown in green here, that path length is different than the path length shown below in red. And the extra path length shown in red, to satisfy Bragg's law, that had to be one wavelength. So the extra path length of beam 3 is going to be a fraction of a wavelength. And that path length difference means that we're going to get some interference effects between waves 3 and 2. How do we think about that? Well, let's start by measuring the path length difference for wave 3. Right, that's going to be dE plus EF. And we calculate that exactly as we would in Bragg's law. The angle theta is the same, and the only thing that's changed is our hypotenuse here of our right triangle is now x instead of a. But we could also write x in a different way. When we talk about atoms in a crystal, we oftentimes will use fractional coordinates. Like you might say in a body-centered crystal that you have an atom at half, half, half. What you mean by that is half of the A lattice vector plus half of the B lattice vector plus half of the C lattice vector. And we get those fractional coordinates by dividing the distance something is displaced from the origin by the lattice vectors. So to write the position of this second row or plane of atoms in fractional coordinates, we take x and divide it by the lattice spacing A. And we can incorporate that into our path length equation. Let's just replace x with the fractional coordinate u times the lattice parameter A. All right, so now we have the path length differences for waves 2 and 3 from wave 1. What is the path length difference between those two waves? Well, here are the path lengths. We've calculated them. And so let's say that the path length of wave 2 is here, 2a sine theta. We're going to subtract from that the path length of wave 3, which is 2 ua sine theta. We can remove a 2a sine theta, which is common to both terms, and then that leaves us a 1 minus u. We can then note that 2a sine theta, the extra path length of wave 2, well, that's equal to the wavelength lambda. That's the basis of Bragg's law. But to use our newfound skills with combining waves, it's actually more convenient not to have the path length difference, but to think about the phase difference between these two waves. Right? Because they travel different distances, they're going to be out of phase by some amount. And we can convert from a path length to a phase shift or phase difference by taking the path length, dividing by the wavelength, and multiplying by 2 pi. Right? If the path length difference is the wavelength, then we've shifted the wave by 2 pi radians, or 360 degrees. And so when we do that, we plug in our path length into this equation, we come up with a phase shift that's 2 pi times 1 minus u. Well, let's now do our wave addition. Right, so if we have a fractional coordinate of 0.2, that means the phase shift is 2 pi times 1 minus 0.2, so a phase shift of 1.6 pi. All right, so we can draw that. Here's our original wave. This would be the wave that would be scattered off of the top row of atoms or the bottom row of atoms. And then our second wave, and this is the waves that are scattered off the atoms that are not at the corners of the unit cell. And it's the same amplitude because they're the same atom, but it's shifted by 1.6 pi or 288 degrees. Now if I add these two waves together, I get a new wave, which I show here. We see that the amplitude is 1.62, so that's telling us that it's not quite like the two waves completely adding together, but there is some addition between the two. And the phase shift is 1.8 pi, really sort of halfway between 1.6 pi and 2 pi. All right, let's put that intermediate layer of atoms at a different place. What if we were to put it at the halfway point between the two layers? So if we put it here, then the x is now bigger. As I've said here, we're trying to put it halfway in between, so the fractional coordinate u becomes 1/2. So when wave 3 comes in and is scattered off of this middle row of atoms, the path length difference is going to be this dE plus EF, this green line, right? And that we can calculate, and just as we did on the previous slide, the only thing that's changed is now we have a different value for our fractional coordinate u. It has increased. And if u is 0.5, then we're going to get a sine theta. So we can see just right away at looking at this that the path length of wave 3 is only half as big as the path length for wave 2. And that means that we're going to phase shift this actually 180 degrees out of phase, right? If we look at the wave addition of combining these waves now, our phase shift is 2 pi times 1/2, so that's just equal to pi. Right? Pi in radians is 180 degrees, so what it means is that wave 2, which is shown in red, is exactly out of phase with wave 1. And when we add these two waves together, they completely cancel. Right? So the resultant wave is complete destructive interference. So we see that there are certain places in the unit cell where you might put an atom, and it would completely cancel out the scattering from another atom because it scatters with a phase shift of 180 degrees. And we'll see a little bit later in the lecture how that comes back to the idea of systematic absences. Now what about if that middle layer of atoms was actually a different atom? What if it was a heavier atom? Well, what would happen then is, the path length difference would be the same. Right? The math on this slide is exactly the same because, we have not put this atom in a different spot. It's in exactly the same spot. But because it's a heavier atom, it's actually going to be more effective at scattering X-rays. And that's going to give it a larger amplitude. So when we go to do our wave combination, for illustrative purposes here, let's double the scattering power of these purple atoms. And so that means this wave, the red wave, is bigger than the blue wave. And when we add these together, although there is destructive interference, it's not enough to completely cancel the wave out. So the new wave has an amplitude that is just the scattering power of the purple atoms minus the scattering power of the black atoms. And so that's not zero. That's a few illustrative examples. I could do more. We could do some math, and I could put atoms at a general XYZ position, and we could look at different planes of atoms. But if I did that, it would actually be several minutes of derivations in trigonometry. And we're going to take a shortcut and just look at what the result would be. And that is shown here. The phase shift for an X-ray that's scattered off of an atom that's not at the origin, but at some general point in the unit cell with fractional coordinates u, v, and w, will be given by this formula, 2 pi times hu plus kv plus lw, where h, k, and l, those are the Miller indices that define the plane of atoms that's doing the main scattering, right? That's what we would put into the Bragg law to determine the angle theta at which the X-rays are coming in and out, right? So this phase shift would be with respect to an X-ray that's scattered off an atom at the origin of the unit cell. Now, we could express this wave that's scattered off this atom in our complex number notation. We could say, all right, we've got a certain amplitude of this wave, and that's multiplied times e to the I phi, where phi is the phase shift. The amplitude is just going to be the scattering power or the atomic form factor of the atom on that site. And then this expression up here tells us what the phase shift phi is going to be. So we're going to have one of these terms for every atom in the unit cell. And if we do that, then we would end up with an equation that looks something like this. If we have n atoms in the unit cell, we're going to have a series with one term for each atom. And each term is going to be the scattering power of that atom times e to the I 2 pi, and the term in the exponential is going to be derived by two things. Where the atom is located in the unit cell, that's given by u, v, and w, and the theta angle of the X-ray coming in that satisfies Bragg's law, and that's given by the h, k, and l. Now, when we want to talk about how strong this F is to the intensity of that certain Bragg peak, we're going to take this F, H, K, L and square it. Right? And since it's a complex number, that means multiplying F times its complex conjugate. All right, so now we can come back to our grand equation for peak intensities, and now we know how to get this F, H, K, L in principle anyway. The other terms we discussed in the last lecture. So now we know everything we need to know to calculate the intensity of any peak as long as we know the crystal structure in question. So let's do some examples. At this point, this might seem a little bit esoteric to you, a little hard to grasp, maybe conceptual, but I think if we do some examples, it will become a little bit more clear how we use this math. Let's go back to our example of polonium. Right, this is the uber simple example that we used in the last lecture to talk about all those terms that were not the structure factor. And at that time, I told you, the structure factor for this particular crystal structure is going to be the same for every single peak in the pattern. Let's see if that's really true. Okay, so this is a primitive cubic unit cell. There's only one atom in the unit cell. and the coordinates of that atom are 0, 0, 0. The structure factor for any given peak is the atomic form factor for polonium times e to the I 2 pi times h times u plus k times v plus L times W. But UV and W are 0, so the term in the exponential goes to 0, and we end up with the form factor of polonium times e to the 0, and e to the 0 is 1, so that's just the form factor of polonium. And in our intensity equation, we're going to square the structure factor, and so just as I promised, all of the peaks have the same structure factor, and it's given by this number. Now, of course, the atomic form factor of polonium does drop off as we go to higher angles, but the structure factor itself doesn't change. All right, let's do an example that's a little more complicated. Let's at least have a second atom in the unit cell. Now we have the opportunity for either constructive or destructive interference from waves that are scattered off the atom at the origin and the atom that's at the body center. The example that I'm going to use here is tungsten. All right, now we have two atoms in the unit cell. One at the origin, so U, V, and W are all 0 for that one, and one at the body center, where U, V, and W are all 1/2. In our structure factor equation, because there are two atoms in the unit cell, we have two terms. Because both atoms are tungsten, the amplitude of the waves is going to be the same, the atomic form factor of tungsten. But because the UV and W are different, this phase shift will be different. Right, so the first one, the 0, 0, 0, gives us an e to the 0, which is a 1. So our first term is the atomic form factor of tungsten. And for the second one, we've got half, 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 which when we multiply that by 2 pi, right, it's common, we can bring it out, we just end up with e to the I pi times the sum of h plus k plus L. To further simplify this, let's just remind ourselves of a couple of relationships that we can use. E to the I pi, we could also write that as cosine pi plus I sine pi. Well, pi, right, that's 180 degrees. So cosine of pi is -1, and sine of pi is 0. And so e to the I pi is not a complex number. It's a real number, and its value is -1. And that's also true for e to the I 3 pi, e to the I 5 pi, e to the I times any odd integer multiplied by pi. And of course, h, k, and L are all integers. So when we sum them, we're always going to get an integer. And if that integer happens to be an odd number, then this whole term is going to become -1. If it's an even number, like 2, then we would have cosine of 2 pi plus I sine 2 pi. 2 pi is 360 degrees, so that's just 1 plus 0, which is 1. And that's what we're going to get every time the sum of those three integers is an even number. E to the I 4 pi, e to the I 6 pi, e to the I 24 pi. All of those are even numbers times pi, and so they all give a value of 1. With those relationships in hand, let's go back to our structure factor equation, and let's first of all look at what it reduces to whenever h plus k plus L equals an odd number. In that case, we just get a -1 out of the exponential. We end up with the form factor of tungsten minus the form factor of tungsten. And so that is precisely 0. And if we were to square it, 0 squared is still 0. So what that tells you is that the structure factor for all of the peaks where those three integers add to an odd number is going to be 0, and the intensities are going to be 0. Remember that the reflection condition for a body-centered lattice is all of the peaks are going to be missing when h plus k plus L is odd. So the reflections that we see, the reflection condition, are only h plus k plus L being even. And now that we look at this detailed calculation of the structure factor, we can see why. The other kind of peaks are those where the sum of those three numbers is an even number, And in that case, the exponential just gives us a 1, and FHKl reduces to 2 times the form factor of tungsten. And the square of that is then just 4 times the form factor of tungsten. So when we look at that pattern for this body-centered cubic metal, tungsten, if we were to compare that to the polonium one, we would see, all right, actually there are fewer peaks. It seems like almost every other peak is missing. And now we can see why. Because the peak that might have been at 100 or 111, those have a structure factor that's 0 and they are absent from the pattern. All of the peaks that we see here have exactly the same structure factor, 2 times the form factor of tungsten. So the intensity variations we see here are strictly due to differences in the multiplicity. And we can also see how those reflection conditions or systematic absences that we discussed a few lectures back actually come out of the structure factor calculation. Let's do one more example. In this example, I want to go to something that's closely related to a body-centered cubic metal, but here I'm going to pick a compound that has the cesium chloride structure. Specifically, I'm going to pick cesium bromide. Right, so we still have an atom at the body center, but it's not the same as the atom at the origin. Here we have cesium at the origin and bromine at the body center. And compared to that pattern we just looked at for tungsten, now we do see more peaks in our pattern. But some are very weak and others are quite strong. And that variation in weak-strong doesn't really look like the variations we've seen that are due to multiplicity. So where does that come from? Well, let's calculate the structure factors. The two atoms in the unit cell are cesium at 0, 0, 0, bromine at 1/2, 1/2, 1/2. So our FHKl structure factor equation is going to have one term for cesium, one term for bromine. Now, because cesium is at 0, 0, 0, the exponential just drops out, and the bromine, being at 1/2, 1/2, 1/2, gives us this I pi times H plus K plus L. Right? This looks just like our structure factor equation for tungsten, for the body-centered cubic metal, with one important difference. And that difference is that the amplitudes of the two waves are not the same. Cesium is heavier than bromine, so that means that the amplitude of this wave is going to be bigger than the amplitude of this wave. Now, we still have the same kind of effect of sorting the peaks into those where H plus K plus L is an odd number and those where it's an even number. When it's an odd number, that exponential becomes -1, and we see that our structure factor is the form factor of cesium minus the form factor of bromine. Right? So they are destructively interfering, but because the two waves have different amplitudes, they don't entirely cancel out. When H plus K plus L is an even number, then the exponential goes to a 1, and we get a structure factor, which is the form factor of cesium plus the form factor of bromine. Now, scattering off of the two atoms leads to constructive interference for these peaks. And so that really explains this intensity variation we see in the pattern. So the 1, 0, 0, the 1, 1, 1, the 2, 1, 0, in all of these cases, H plus K plus L is an odd number. And that means the structure factor for these peaks is going to be the difference between the scattering of cesium and the scattering of bromine. And notice that these three peaks are all quite small. Whereas the strong peaks, like the 1, 1, 0, the 2, 0, 0, the 2, 1, 1, the 2, 2, 0, these strong peaks are ones where H plus K plus L is an even number. And so in those cases, scattering off of bromine, scattering off of cesium is constructive. They're adding together. And that's what makes these peaks stronger. Now there are still intensity variations due to changes in multiplicity, the drop-off of the form factor, the Lorentz, and the polarization corrections. But those other terms outside of the structure factor can't tell us why the 210 peak is weak and the 200 peak is considerably stronger. Right? The multiplicity here is 4 times that of this one, but yet it is a weak peak. And if you were to carry this to its extreme, imagine that the scattering of cesium and bromine became closer and closer together. That is, we made atomic substitutions, so their atomic numbers got closer and closer together. When they become equal, the structure would simply be a body-centered cubic metal. And in that case, the intensities of these weak reflections would go to zero. They would become systematically absent.